All right, so we talk about monoalphabetic substitution like Caesar cipher and affine cipher. Now, we mentioned that their key spaces are not that large, right? Because we were talking about small key spaces. Question is, can you still do monoalphabetic substitution? I mean monographic, so one letter with one letter substitution, but still have a very huge key space. The answer is yes, and this is called simple monoalphabetic substitution. And the encryption algorithm is every letter is replaced by a letter. So you write your alphabet here. I wrote the English alphabet. So I randomly permute these keys. So I write the alphabet in a random order. And I say that this is my key. And I also give this to the person I want to communicate in a secure way, maybe physically by hand. Then say that, okay, this is how we are going to communicate. So this is how it is done. You write your documents, then take another paper, and in your original document, whenever you see A, you replace it with K. Whenever you see B, you replace with U. Okay? So this way it looks like something random. Okay? And the person who receives your ciphertext, they already know the key. So whenever they say they observe K, they will replace it with A. Whenever they say they see U, they will replace it with B, and so on. They will convert the ciphertext back to plain text. So question is, how many keys I can choose from, right? Since the alphabet has 26 letters, in front of A, I can write 26 different letters here. So once I choose one, here only 25 options remain, 24, 23, 22. So if you multiply all of them, this is actually equivalent to 26 factorial. And this number is, as you can see, very huge, right? So if you have this many possibilities, then you cannot perform brute force attack by hand, right? So this is why for a very long time, people use this kind of encryption algorithm in the past. And it was secure for a very long time, but then it got broken, okay? So not by performing brute force attack, but by performing the frequency analysis, which is a very clever way to attack the system. So here the weakness in this algorithm is that the redundancy in the language. This means that there are some repetitions in the language, which creates actually a statistical weakness. So frequency analysis is a statistical attack, and in modern cryptanalysis, almost every attack is statistical. So you have to learn frequency analysis and perform it to understand how modern cryptanalysis works, okay? So let's look at what the redundancy here is and how we can use it, okay? So here's an example. I wrote something in English, then I use monoalphabetic substitution. So the ciphertext looks like this, okay? As you can see, when you look at it, it looks like random. And you cannot come up with a very easy way to say that, okay, I can convert it to plain text like that, or maybe it is written this there. As you can see, you cannot say it, right? There are some things like you can say that, okay, the H is next to H, so the same letter appears here, but maybe there's a space here, so maybe this is the last letter of a word and this is the first letter of a word and so on. So you don't have anything, right? So it looks like something unbreakable because there are many. The key space is really large and you don't see any easy way to do it, but there is actually a very easy way to do it because, as I mentioned, there's a redundancy in the language. So let's see what it is. Frequency analysis is introduced by Al-Kindi in a manuscript deciphering cryptographic messages, which is a manuscript written in 9th century. So this is actually the, as far as I know, first cryptanalysis document we have. Okay, so historically this is the oldest, and as far as I know, there is a copy of it in Topkapı Museum. So if you go there, you can see it, and if you pay some money, you can take the photocopy of the pages of this document. Okay, so it is explained like this. It is based on the redundancy of the language, and they say that some letters appear more frequently than other letters. So question is how I can determine this and how can I use it to break the system. So idea is as follows. For a given language, find a long text, and count the number of frequencies of every letter. Okay, so for instance, take a novel and count how many times A appears, how many times B appears, how many times C appears. All right, then order them from larger to lower, and you will see that which letter appears the most in that language. So if you divide them to the number of letters, then multiplied with 100, you will get the percentage of these things, right? So if you do it, you will observe that in English, E is the letter that appears the most. And the second place belongs to T. I forget the percentages, but maybe 12% E, 10% T, and so on. Okay. So how are you going to do after you obtain these percentages? How are you going to decrypt a ciphertext? You take the ciphertext, and if it is long enough, you count the letters in the ciphertext. So you go back here, count all of the letters appearing here. So in the ciphertext, if you know that it is written in English, for instance, maybe you count all of the letters here and you realize that H appears the most. Since H appears the most, and you think that it is written in English, you will replace every H with E because it appears the most in English, right? So this is a statistical guess. Sometimes you may fail because here you get the percentages by, looking at a very long text, but maybe your ciphertext is not that long enough. Maybe the context is different, so the percentages might change. So this is a trial and error game. You replace the letter in the ciphertext that appears the most with E, the second most with T, and you look at it, and by every change you look at it and try to see if something goes wrong. If something goes wrong, you replace the orders and so on. But at the end, you generally obtain the plain text. So this is in the past, this was something hard to do because you have to take, for instance, 300-page book and count every letter. But today we have computers. Just write a simple code and count all of the letters. I did it using the Perl language, which is very nice. But currently, you don't even have to do it. Take the text document, open it with Google Chrome or Mozilla Firefox, and search for the letter A, and it will say that it appears like 40,000 times or something. So you don't even need to write a code. You can look at every language, take a very long document written in that language, French, Portuguese, Turkish, whatever you want, count all of the letters, and then, obtain the frequencies. And this way you can actually break those ciphertexts encrypted by the monoalphabetic substitution and used by that language. Okay, so this is a very nice example, a very nice exercise, finding the frequencies in a language, and it is very easy to do nowadays. And then you can also check the frequencies of pairs of letters, triples of letters, so that actually you can break this kind of substitutions because there is a redundancy in the language. So the ciphertext also has that redundancy. This is why frequency analysis can break this kind of simple substitutions. This is why we need to come up with a better technique. Okay, we need to come up with a better way of substituting letters, not by simply substituting one with the other, but we should come up with a better algorithm. So next time we will talk about Digraph substitution by using the Playfair cipher.